All right. So second part, we have the concept of measurement, error, and uncertainty. So first, we have to clarify these things by defining them. Measurement is the process of assigning a value to a physical quantity. Okay, so when we measure a certain physical quantity, like temperature, we are actually saying, okay, when we measure that, okay, the temperature is this much. Okay, because you measured it and that number appeared on your measuring device, then that's the number that's the value you are assigning to that quantity. Okay, so measurement. But when we say there's an error, then there we are actually saying there's a difference between a measured value and the true value. So the true value is something that we can say the applicable, or I mean the acceptable value, the one that is believed to be true, or the one that's believed to be correct. Okay. Uh, in some cases, true value is derived only by taking the mean of a series of values. Okay. Some people also just set a standard that this is the true value because this is the accepted value. Like this is the standard value. Okay. So if there's a difference between your measurement or your true value, which is normally the theoretical one, the one you calculate, if there's a difference between that, then we can say there's an error. Okay. Now, to prevent that or to have at least to provide some allowance in our measurements, we we consider the concept of uncertainty. So wherein we put a range, a plus minus value, around a measurement that indicates the doubt in the result, reflecting all sources of error. So, um, for example, you measured 1,000 resistors. You measure their individual resistances, and they are meant to be, let's say, they are meant to have 1 kilo ohm resistance. Okay, that should be the true value. But upon measurement, many of them or most of them are not exactly 1 kilo ohm or 1,000 ohms. So now, given those values, you can now come up with a certain range. Okay, so you can say a plus minus 5%, which is one of the most acceptable tolerances in the measuring or in resistors. So you can have a range, and that range would indicate that there's no certainty that the value you get is exactly like the true value or the theoretical value or the accepted value. Okay, there could be a slight difference, right? Because it is within the range. So if it's within the range, then it is somewhat acceptable. Okay, so the error is still manageable. Okay, and but whenever we put an certain range or like a tolerance range, a plus minus value, then we are actually saying that there's no assurance that the measurement that we're getting is equal to our expected or the calculated value. Okay, so I hope you get these terminologies. All right, so we have three cases here. um Kindly observe na lang. Okay? Because next slide, we have here the concept of accuracy. So accuracy is an overall concept often used informally. Sad to say, many say this thing is accurate when he or she is actually saying that it is uh, reliable or it has a high precision. Okay, so remember, accuracy is more technically a combination of trueness and precision. Okay, so meaning it has a very true value, or it is very close to the true value, and it is very precise, meaning something like consistency. Okay, so um, a measurement can be accurate with large uncertainty. For example, that that means we can have right answer, but we have low confidence because there's a high uncertainty, meaning the values could range much or could deviate much from the true value. Okay, but we can also be inaccurate with small uncertainty. We can have precise values like what we have here on the right side, precise because they are close to each other. Okay, but they can be wrong. They can be far enough from the true value. Okay, so um what we want is just enough trueness, as you can see here. They are very close to our intended value. At the same time, very high precision. They are very close to each other. Okay, very close to the true value and very close to each other. So all the measurements that we have are very close to each other. So if that happens, then that could be the only time we can say it is accurate. Our measurement is accurate. Okay? Because accuracy can only be judged when the true value is known. Okay, like this one, the true value is here. Uh, but uncertainty can be reported even when it isn't. Okay, so I hope you got the terms right. You at least you have a better understanding when you next time you use these words. Okay. Also, in engineering, one of the most common things that we compute when taking measurements is the percent error, or sometimes we call it the percent difference. So actually, there's a thin line that differentiates these two. Okay, if we were going to be more technical, so percent error is actually the one that measures how far a measured value or the experimental value is far is from a known or accepted true value. Okay, so we just basically take the difference and then divide by the accepted value or the true value, and then times by 100 percent. Okay, so that's the percent error. So meaning the the smaller the different right, the smaller the difference between the accepted and the measured values, the smaller the error. Okay, and that's what we want, a very small difference. Okay, what we measured is actually what is somewhat close, very close to the true value. Okay. Um, but sometimes we use the term percent difference, which is somewhat very similar, but it is technically the one that measures how different two measured values are from each other. So sometimes one of those two values is the true value. Sometimes it's not. Okay, none of them is the true value because you can take the percent difference even if you don't know the true value. Okay, because percent difference is also treated like percent error when one value, though not the true value, is considered a reference value. Okay, so it depends on your experiment. It depends on the scenario. If you have two values being compared, you can consider one as the reference that could somehow be treated like the true value, and then one is the other one is your measured value. So just like here, you just take the measurements, I mean the difference between the two, and then divide by what do you consider the reference value, and of course times 100%. So if you don't do that, then technically when we say percent difference, this is what you need to do. If none of them can be considered a reference value, then instead you should take the difference between the two values and then divide them by their mean. Okay? Because the mean could be the true value. Okay, if you don't know the true value, you can come up with uh, uh s- an approximate true value, which is the mean. Okay, so that's it. I hope you got the difference between the two. Now, to be more accurate in our measurements, we normally use the significant figures, or we consider the concept of significant figures, or the digits that carry meaningful contributions to its measurement resolution. And there are three rules for this on determining how many significant figures are in a number. So, rule number one, non-zero digits are always significant. Okay? So, as the moment you see a non-zero in a given number, like this one below, so 1, 2, 3, and then the 4, 5, 6 are all non-zeros. Therefore, automatically we have six significant values already. And rule number two, any zeros between two significant digits are significant. Okay, so we already mentioned that um, any non-zeros are significant. So meaning everything between non-zeros are already significant. Plus everything, um, we have the third rule, a final zero or trailing zero in the decimal portion only are significant. So as you can see here, the leading zeros are never significant because what we consider are the trailing zeros, the ones at the right. And in addition to numbers 1, 2, 3, 4, 5, 6, we can add these three, the trailing zeros, plus these three between the non-zeros, because captive zeros, or the zeros between non-significant, um, between non-zeros, as you can see, for example, here, the three zeros between the 3 and the 4 are all significant. Okay, so meaning, um, in this example, we have a total of 3 plus 6 plus 3, so 12. Okay, for this example, we have 12 significant figures. So if we have that much, then we should be cautious when we are rounding off, or when we are expressing, or maybe writing the numbers, because we should um make sure that they are all accounted for, they are all recorded, right? Because we consider them scientifically, we consider them significant, right? According to our rules. For other examples, 2003 has four significant figures because 2 and 3 are non-zeros, okay? And then two zeros in between them are also significant, okay? Because they are between the two non-zeros. Next, we have this number. So it has three significant figures, because um, all the zeros on the left are not included. So the first non-zero here is significant. So count the three. That's the first one. And then remember rule number three, trailing zeros are significant. So the two zeros after the three are also significant. Okay. Third one, as you can see, we have a trailing zero also, but this time it's no longer counted because there's no decimal point in this example. Okay, so only uh meaning uh all the zeros that we have here are on the left side of the decimal point, which are all not counted unless the zeros are between two non-zeros. So here we don't have any non-zero after these zeros. We don't have any number to sandwich them. Okay? But we have only 6 and 7 sandwiched between the sequence of zeros. So only these two numbers are significant or digits. Um, while here, since we have our decimal point here, then we now have six significant figures. Okay, why? Because 6 and 7, and then the trailing zero, okay, we have three. And although it was not mentioned here, um, doesn't have to be a non-zero that will sandwich the a group of zeros. So here these three zeros are considered significant because they are sandwiched between a non-zero and the decimal point. Okay, so they are all counted. So one, two plus the three of them plus the trailing zero. So we have a total of six significant figures. Okay, so this is just one of the examples or the ways that we become more um, cautious when dealing with our measurements. Okay, we have to observe the significant figures in our measurements before we decide to round them off or to um get rid of what we consider insignificant. Okay? Remember these rules. Okay. And in addition to that, usually we apply this in the when we are doing scientific notation or when we are writing numbers in scientific notation. So which is this is a way of expressing numbers that are too big or too small to be conveniently written in decimal form. So for example, okay, we have let's zoom in. Okay. We have no numbers that are very big. So for example, if we have 620, the number, second example, if we have 149,600,000, you can actually conveniently write it as 1.496 times 10 raised to 8. So it depends on the number of significant figures that you would like to achieve. But normally, um, if there are no specifications, we just write them using this form. Okay, we have a non-zero number here, whether that is positive or negative, and that is followed by, of course, the decimal point. And the decimal point or the decimal point portion or the mantissa, it could be of any length, right? Depending on the significant figures involved in your number or depending on your um in what how many decimal points do you want to keep? Okay, so um the this number and the mantissa are collectively called the coefficient, and they carry out the positive and negative sign. And in addition to that, we have that what we call the base, which has the exponent. So the exponent corresponds to the number of zeros, trailing zeros here. So in this case, we have we can move the decimal point according to the this exponent. Okay, so since we have four, that means we are moving this decimal point four times to the right. Okay, so this number is actually 1, 2, 3, 4. So that would be 47,635. So that's the actual number in regular notation. Okay. Other examples we have here 6.2, as you can see, times 10 raised to 1 only. So we move the decimal point once to the right only. So 6.2 times 10 raised to 1 is actually 62. So we just move once. Okay? But in this case, we have times 10 raised to 8. So we move this 8 times, okay, leading to this actual value. So if you get to the rightmost part and still you have to move some more, then you add zeros, zero, zero until you get the the exact number of movements that you need. So for example, 8 times, then all the movements here will be um, um, replaced with zeros or will be denoted with zeros. Okay. But on the other hand, if the exponent is negative, then we move to the left. So for example, this one, 2.3 times 10 raised to negative 3, then we move it to the left. 1, 2, 3. Same thing, all the movements will be represented by a 0. Okay, so we will insert here because it's 1, 2, 3. So we have two more movements here on the left, so we insert two zeros. So that would mean 0.00231. Okay? To make it more significant, then we add this zero here. Okay? Basically we add the zero to make the decimal point more visible, more obvious. Okay? So I hope you get the what do you call this? The pattern. Okay, remember, we have some rules also in scientific notation. Number one, the base is always 10. Okay, this is the base, remember. The exponent is a non-zero integer. So we can never have zero here because if we have zero here, then it's useless. You can simply remove this part. No need to be in scientific notation. Okay. And then number three, the absolute value of the coefficient is greater than or equal to 1 and strictly less than 10. Okay, just observe. Next, the coefficient carries the sign. As you can see, we have either positive or negative coefficient. The mantissa carries the rest of the significant digits, as you can see. And then to multiply two numbers, multiply the coefficients and add the exponents. That is if they belong to the same exponents. Okay, this is multiplication, so you can do that actually. Okay, just multiply the coefficients, and based on our law of exponents, you basically add the exponents because they all have the base 10. Okay, so remember in the law of exponents, if you have the same base, if two numbers with different exponents have the same base, then you can simply copy the base and then add the two exponents. Okay, so number 7, to divide two numbers the same, just divide the coefficients and subtract the exponent of the divisor from the dividend. Okay, so subtract if this is the denominator and the numerator, the exponents, the denominator's exponent will be subtracted from the numerator's exponent. Okay, and lastly, you can add or subtract two numbers if the exponents are the same. You simply add or subtract the coefficients and keep the exponent the same. Okay. And we have some examples of where do we use normally scientific notations. So actually in physics, we have a lot of constants, physical constants, and those constants are normally written in terms of scientific notation. Okay, many of them are very big numbers or very small numbers. Okay. Again, when it comes to frequencies, like what I mentioned earlier, that's why it's convenient that we use prefixes. But if sometimes instead of using prefixes, we use scientific notation. Okay, when expressing the wavelength, which are very small, or the frequencies, which are very big. As you can see, the wavelength have very negative exponents on their base, while the frequencies have very big exponents. Okay, so these are just some of the ways that we use scientific notation, especially in physics. Okay.